Okay, I guess we can get started. So where is it? Is there an exam or a deadline or something? People have lost interest after the midterm? Probably. Okay. Kalansalar bizim de biliyoruz. Devam ediyoruz. So today I'm going to talk about generalization. We've actually been talking about generalization. So generalization is the holy grail of machine learning. You want to not only do well on the examples on the training set, your main goal is to do well on examples never before seen. So we saw phenomena like overfitting and underfitting, and we saw some ways of dealing with them, like regularization and dropout. So I'm going to briefly review these, go over them with an example to build some intuition, and then I'm going to turn to a probabilistic framework that will hopefully give us a better understanding of how these models generalize, why they don't generalize, when they don't, etc. And stop me for any questions anytime you want. So I'm going to start with the very simple regression example and talk about some definitions. What's model capacity? How do we regularize things? How does the amount of training data influence? And show you some pictures that will hopefully make bias versus variance trade-off a bit more intuitive. And then I'll switch to one of my favorite textbooks by David McKay and go over his probabilistic reasoning about generalization, estimation, prediction. Okay, so here's the example that we're going to look at. So the green, the blue dots are our data. This is a regression problem. So x is our input variable, y is our output variable, or well, t in this case is the output variable. And the way this data has been generated is basically by adding some noise to the green function. So the green function is a sinusoid, and we basically pick random x's, and then the noise-free output would be the corresponding point on the y-axis, and then we add some Gaussian noise to it, and that's how we generate the data. So our goal is to predict the value of t for some new value of x. Okay? So if we actually knew how this data was generated, then we could basically have a model that accurately represents everything about this process. In particular, this would be the picture of, for example, the ground truth function and one standard deviation noise around it. So we would have the exact distribution from which this data has been generated. And then, when somebody gave us an x, we would say, oh, most likely I'm expecting the y value to be on this green line, but there's also this much noise around it, so I have a distribution around that y value. So this is the ground truth, and this is the true conditional distribution that we don't know, but we're trying to approximate. And making things probabilistic and representing noise explicitly is something that we need to do to understand this stuff better. Any questions so far? Okay, so the first thing we're going to look at is the data set size. Okay, so here is the same data set that we were looking at, or something similar, for 15 data points. And I'm fitting this with some formula, some function. It's not a neural network, it's just a polynomial of 9th degree. And when I try to fit a polynomial of 9th degree, you see that there is some amount of overfitting and noise. So it's basically trying to curve itself. The red line is the my estimate, and it's trying to fit itself to the positions of the blue points, which means, for example, over here, it's making these moves to get closer to the blue points, which actually makes it further away from the ground truth, which is the green line. Right? But if we actually increase the data points and have 100 over here, even though there's still noise and the blue examples are not on the ground truth green curve, we see that the estimated red curve is a much better match for the green curve. So this is a picture of how increasing the data amount that we train prevents or deals with overfitting. Questions? Okay. So next, I want to look at the relationship between model capacity and overfitting. Model capacity is basically, we can define it as the number of parameters in the model, how flexible the model is. And in this particular case, since we're using polynomials to fit the data, we're going to assume the polynomial degree determines the model capacity. The higher the degree, the more flexible the model, the more complicated functions it can approximate. So on the upper left, we see a 0th degree polynomial. What does that mean? It's just a constant, right? So that's why the red line is a horizontal line. In the next plane, we see a 1st degree polynomial, which is a linear approximation. So if you find the best linear fit to those blue points, you get that red line, which is slightly negatively curved, and it's a horrible fit because it's far away from the ground truth, which is the green. 3rd degree polynomial gives a fairly good fit. Okay, and for this problem, I would say this is sort of the right degree of flexibility, even though it's not perfect. And if we keep going up, we get crazy results like this. So this is a 9th degree polynomial. And since there is very few points, a 9th degree polynomial can hit each of these points exactly. As you see, the red curve is going through each of the blue points exactly. So 0 training error. But in order to do that, it has to bend itself to do these weird, oscillations and moves up and down. And this is a case of extreme overfitting. So here we have underfitting up above, and here we have overfitting. Okay, so these are all subjects that we've seen before, so I'm going over them fast. Please stop me when you have questions. So let's talk about bias and variance. We talked about bias and variance before. So the generalization error, which in this plot has been represented by the red curve, as we found out, is a sum of, can be understood as a sum of two separate things. One is the bias term, one is the variance term. The bias term is basically whether or not the best model in our model set can approximate the real function, or is it far away from the real function, right? So that's the more flexible we make our model, the lower the bias. And variance is basically how much does the model change in response to small changes in the data. And the more flexible a model is, the more it will change. So when we increase the model capacity, let's say the polynomial degree, from very low to very high, we see that the bias keeps decreasing because higher level polynomials can approximate arbitrary functions very well, whereas the variance keeps increasing. And since our generalization error happens to be the sum of these two things, there is a sweet spot in the middle, which here we call the optimal capacity. Okay, so this would be, these could be things like, the x-axis could be things that control the capacity of the model, like the degree of polynomial, the number of hidden units, or the regularization coefficients of a model. Okay. So here's another picture of bias versus variance. So again, I have the green curve as my ground truth. and I'm fitting it, I'm trying to approximate it with the red curve. And these particular red curves come from, let's see, Gaussian basis functions. That's not important. But basically they're regularized, and the regularization parameter right now is, or log of the regularization parameter is 2.6. That's a pretty high regularization. Okay, I'm pulling all these functions toward a flat line pretty strongly. So when we highly regularize a model, we expect high bias, low variance, right? And we expect underfitting, basically. Okay, where we're basically keeping the model too constrained. And here, low variance is seen here. So if I basically generate lots and lots of different data sets from the same underlying framework and try to fit this function to these different data sets, I see that the curves actually don't change too much. They all stick together. So that means the model is fairly stable. Okay? If I use different data sets to train it from the underlying function, I get more or less the same result. That's the sign of low variance. Okay? But over here we see that there's a big difference between the average red curve and the green curve, which is a sign of high bias. Okay, so no matter how much it tries, it cannot approximate the green curve. It's not as flexible because I'm constraining it with a very high regularization parameter. Okay? So again, in the next one, I'm going to reduce the regularization a little bit. So log lambda is now lower. And the effect of this is going to be to increase the variance. Okay, so if you look at the left picture, the different red curves that I got from different data sets are more dissimilar to each other compared to the previous picture. So that means I have a higher variance. When I change the data set, I get more different solutions now because my model is more flexible. But if I actually look at the average of these red curves, I see that it's approximating the green curve fairly accurately, which means at this level of regularization, there is very low bias for this problem in this model. Okay? And we're going to go one step further and decrease the regularization even more. So this is a very low level of regularization now. So the function is fairly free to jiggle around. So since it's free and I'm generating my data from an underlying green curve plus some noise, there's each red curve here basically fits the particular noise in the particular data set that it gets trained on. Okay? It's trying to fit all of those blue points exactly, which makes them jiggle a lot. And in different data sets, they jiggle differently because the noise puts the blue points in different positions. So that basically makes for high variance. If I resample the data, I get very different results. However, if I actually average them, I see again that I'm almost a perfect fit for the green gold truth, ground truth, which shows two things actually: low bias, which is the subject of this slide, but it's also actually showing you an example of ensemble. Right? So instead of training one model, if I actually train 100 different models with slightly different data sets from the same underlying process, and I average their responses, actually the results aren't so bad. Each individual red curve here has a lot of overfitting, therefore its test accuracy is going to be horrible, but their average is going to have a lot better test accuracy, a lot better generalization. That's the second lesson I want you to draw from this picture. Questions? Yeah.
3 slides earlier, we said underfitting, then optimal, then overfitting, but in one of the lectures, I think you said underfitting and overfitting can occur simultaneously.
That's right. So even in the underfitting zone, there is still some fitting to the noise in the training data, possibly. So they're not necessarily mutually exclusive. Any other questions? Yeah.
With neural networks, do we take the average of the test accuracies of different neural networks performance?
When we're ensembling? Yes. So we train independent neural networks, we train 10 of them. And then when we look at the, when we're running on the test data, we basically take the average of their responses.
So here, I mean, each of these thinner curves produce, I mean, if we were to apply the same analogy, would produce low accuracies, I suppose.
On the test set, yes.
And average of all lows would result in a low accuracy.
In a higher accuracy. When you average the different, ensemble different models and average their answers, you would get higher accuracy than their average accuracy. So that so the one simple way to understand this is basically to think of a very simple classification problem. Let's say we're doing binary classification, and we have these really bad models that only have 60% accuracy. Okay, so we did that example, remember? So if these bad models are making their mistakes independently, then by averaging their results together, namely voting with them, we can actually get our test accuracy arbitrarily high. We can get it to 99% if we just keep averaging more and more models, okay, even though individual models are not very good. Now, the key word there is independence. Typically, it's very difficult to create bad models with very independent sources of error. They will all tend to become dependent and make errors on the same examples, which basically puts a limit on how much improvement we can expect from ensembling. But in practice, people always try ensembling as the last resort to get the last few percent in order to get published, as I mentioned earlier. Any other questions? Okay, so we talked about regularization, so we know regularization prevents overfitting, and in this example, this is the earlier model where we're actually fitting a 9th degree polynomial, which, as we saw in previous slides, were wildly swinging in order to match all these blue dots. But if we actually have the right amount of regularization on top of this 9th degree polynomial, even though we still have very few data points, we only have 10 data points, I think, we can get a pretty high accuracy on the test set. If we regularize too much, then we're constraining this 9th degree polynomial to be almost a line, so we're not getting very good accuracy. So somewhere in the middle, we can get good results with an intermediate level of regularization. Question? So we've seen the L2 regularization before, where we're adding the squared norm, the L2 norm of the weights to our loss function, multiplied by some coefficient. And if you actually look at the derivative and look at the steps that SGD is taking, this has the effect of shrinking the weights at every step. Okay, so the weight updates become your regular weight update. Epsilon is the learning rate, and here's the gradient of the loss with respect to W, plus this term, which is 1 minus the learning rate and the regularization parameter times W. What does that tell you? So you basically take the existing W, you multiply all the weights with, let's say, 0.9, so everything shrinks towards 0, right? So if this thing is 0.9, let's say, and then you also move in the direction of the gradient, or opposite that direction. So weight shrinking and L2 regularization are one and the same thing. It's also known as ridge regression, weight decay, Tikhonov regularization, etc. Here's a picture illustrating how L2 regularization sort of works. So in this picture, we're looking at the weight space. We have two separate weights. So we have a two-dimensional weight vector. And in the middle here, oops, around the origin here, what we have is the L2 norm, sort of plotted in as contour plots, right? So the L2 norm of 0 is the best, and the L2 norm of larger and larger circles are getting worse and worse. So the dotted lines represent the L2 norm. The solid lines represent the actual loss. So without regularization, the best loss we can achieve is up there with W star, okay? And there is some sort of contour plot. There's some sort of fitness landscape or objective function landscape around that W star. So what happens when we add regularization? Well, we have to trade off between being close to the origin and being close to W star, okay? And this trade-off basically lands you somewhere at W tilde, which is at a point where these two contour sets actually parallel each other, okay? And if you notice, W tilde is going to be closer to the origin on the x-axis than the y-axis. And the reason for that is the curvature around the x-axis is lower and the curvature along the y-axis is higher of the actual objective function.
John,
Yes?
so I understand this L2 regularization is helping to keep the V's smaller somehow,
Yes.
but I don't understand how does this help with overfitting.
Good question. So, ask me that question again when I actually do the probabilistic analysis, because I think that's the right way to understand it. Yes?
Why aren't we specifying alpha values, alpha values, L2 values that are specific for different weights? Yeah, alpha.
So the dotted contours are the L2 values for different weights.
Well, the dotted contours are perfect circles. Why are
Yes.
we doing them in ellipses?
Because it's L2, which means W1 squared plus W2 squared.
And we,
So that actually describes a circle. Right? So if you had different weights on them or something, you might get ellipses, but
yes, that's what I was.
But L2 norm, by definition, is basically circularly shaped for a vector space. Okay. One side note is we usually recommend early stopping when you're training your models, which means as you're training epoch after epoch, you keep checking your performance on a dev set, a validation set, and after a while you will see that the model will start overfitting, and even though the training set loss will get lower, the validation set loss will start getting higher, and at that point you should stop. Okay, so that's a common trick that all neural networks trainers use. And here sort of you see the effect of that. So I start at the origin, I'm moving toward the W star during my training, okay, in this weight space, following the gradients. And at some point, I basically start noticing overfitting on my dev set, and I stop training at W tilde. And that W tilde can be also seen as basically corresponding to the W tilde that I get from a certain amount of regularization. Okay, so early stopping is a kind of regularization. So this might be one little answer for the earlier question of why regularization helps. So if you were to try early stopping, for example, initially you would initialize your weights with random small numbers, so your weight norm would be low. And then if you actually follow your weight norm epoch after epoch, you would actually notice that it increases at every epoch. And at a certain point, it would actually start overfitting, and you would stop training there, which would correspond to this W tilde. Now, there's also L1 regularization, also known as lasso regression. And here, the only difference is instead of adding W squares, we're adding the absolute values of the W's. And it gives qualitatively different results for some problems. In particular, after applying L1 regularization, you will notice that a lot of weights will go to 0. So you will have a sparse weight vector, which is not the case with L2 regularization. In L2 regularization, a lot of weights might go to very small values, but they will not be exactly 0. So if you want sparse solutions, then L1 regularization is the one to use. And here's a picture that illustrates why one of them drives weights to 0, whereas the other one only makes weights smaller. So to the left is the previous picture we saw, or something close to it, that demonstrates the L2 regularization. So the orange circle represents a contour of the L2 norm of W, and the blue circles represent the actual objective function, and you stop somewhere between the origin and the W at the center of the blue circles if you use L2 regularization. Okay? Now, if we use L1 regularization, what do the contours look like? L1 regularization is what? It's absolute value of W1 plus absolute value of W2. So if you keep that constant, the type of contours you will get will be these diamond-shaped contours. Okay? Of course, in n dimensions, but here, in order to visualize it better, you can see it. And when you have a diamond-shaped contour like this, it is more likely that a particular blue objective function is going to be tangent to that at a particular axis, at the tip of this diamond, than somewhere in the middle. Okay? Which basically tells you that here, for example, W1 is driven to exactly 0, whereas W2 is the only one left. On the left, W1 was only pushed to a very small number, but not exactly 0. Okay? So, thing to remember from this is L1 regularization will give you sparse solutions, which might generalize better for some problems. So I'm going to go over a few tips and tricks to improve your generalization accuracy. The first batch of tricks that I have is all about adding noise to various things in your training. Okay? So add noise to your data set. So this could take the form of creating fake data and adding it to the training set. So that's also known as data set augmentation. So if you're working with MNIST, for example, you take each image and then you apply various rotations and scalings and shiftings and blurrings, etc. to it without changing the actual class of the digit. And you add all of those things into your data. So now instead of having 60,000 examples, you have 6 million examples, which helps with generalization. So if you don't know anything, I mean, in MNIST, we sort of know that sort of shifting something slightly or rotating something slightly is not going to change the digit. But it might be hard to come up with operations like this in every problem. If you don't know your data, just add some random noise to the input, which is something that dropout does, for example, for you. You can also inject noise to the hidden layer activations. Again, dropout does this, a particular type of noise. You can also inject noise to the weights. At every mini batch, you basically instead of using the W, you're using W plus some Gaussian noise? Yes.
I was about to ask this. Is it dropout or Gaussian noise?
This is general. Dropout is a specific case of
Case
this.
of it, just noise.
Correct. And dropout adds noise to the inputs or the activations. It does not add noise to the weights. Adding noise to the weights has a different connotation that we'll see later. So adding noise to the weights will force your training procedure to be robust to small changes in weights. So it will end up finding solutions in the weight space which are pretty flexible. So if you change the weights slightly, your performance doesn't decrease too much because it's been trained for being able to be noise tolerant. And we'll see at the end, hopefully, that being in a region of the weight space where things are not very sensitive to small changes in W is a good thing. We'll see that at the end of the lecture. And finally, what else can we inject noise to? Output, right? So we added noise to the input, we added noise to the activations, we added noise to the weights, and also sometimes we might add noise to the output, which helps you both model label noise, which some data sets may have a certain percentage of wrong labels, so each of these tricks have been used to improve generalization. Ensemble methods we talked about, so I'm going to skip over that. I will give you one specific example of an ensemble method called bagging. Bagging is short for bootstrap aggregation. So here, if you have 100 samples, for example, you create different data sets by sampling with replacement from these 100 samples. What do I mean? Basically, you take the 100 unique instances and then you pick 100 instances from that with replacement. Okay, so since you're doing it with replacement, some examples will be chosen more than once. But in general, you can calculate that 67% or something of the unique examples will end up in the final data set. Okay? And then you do this again and again and again, and each time you're basically seeing another new 67% of the examples, so each data set becomes slightly different. So that allows you to train different models with each of these data sets. So remember the wiggly red lines that we discussed in the bias variance example. So for each data set, you will get another one of those wiggly red lines. And at the end, when you average the results of these things, you can get a boost in test set accuracy. So here's sort of a very artificial example of why this might be working. So let's say you have a MNIST type of data set with 3 digits, 9, 6, and 8. The first time you sample from this data set, 9 gets dropped out, and you have a data set that has 8 and 6. Okay? You train on this data set, and your network learns that, for example, if there is a circle up top, then that's an 8. If there isn't, then that's a 6. Right? You sample it again. This time, by luck, you get 2 9s and no 6s. And your network learns that a circle in the bottom this time is the important thing for an 8. Okay? So both of these models are not very good by themselves because they will actually get confused in the full data set. But if you use them together and average their results, add their results up, then they will actually predict 8 fairly accurately. Okay, so that's the general idea. And this is one way to create an ensemble of models. We've seen dropout, which is basically adding noise to input and hidden activations. There is also a way to interpret dropout, especially when you're doing Boolean noise. as canceling out some of the units. So if this was our base network and I was using dropout, then what happens is some of these weights are going to get zeroed out. That means some of these units are going to drop out of the picture, and after the dropout is applied, I might end up with a subnetwork that only has some of the units in my neural net. Okay? And since every mini batch I change my noise, I end up with a different subnetwork. So one way to understand dropout is basically we're training all these subnetworks simultaneously by optimizing a different one for each mini batch, and at the end we're using all of them together, so there's an ensembling effect, and they basically increase generalization through this assembling process. Okay.
That was a one network without any input layers, but only with hidden and Y. So how does one train that? In the previous slide. I mean, there are some of them without any weights.
What happens is basically all the x's get zeroed out, right? So in this network, for example, the x weights actually got dropped out. It could happen. So then, same thing. You basically, have an h1, which is probably 0, and then it predicts some y, and that y might be right or wrong, and you flow back your gradients, and every w, every weight array, which was active during that decision making, will get updated.
And will help with the final decision.
Presumably, yes.
But it seems like it doesn't have any knowledge of the relationship between x's and y's.
Then you can think of it as learning an average result. So if I didn't know anything about the input, what would my average result be? Right? So even that's sort of useful information. Okay, now, I think in order to really understand generalization, overfitting, all these things, a very useful thing to have in our toolbox is a probabilistic perspective and probabilistic analysis. So I'm going to review probability theory in 2 slides, and then we're going to apply it to all this stuff we've been doing since the beginning of the semester of creating models, training them with data, trying to estimate new data, etc. So remember that all probability theory is derived from these 3 axioms. These are called the Kolmogorov axioms. So probabilities between 0 and 1, they have to add up to 1. And then if you have a disjoint set of things, then their probabilities add. You can derive everything in probability theory from these and the definition of conditional probability. Here are some useful things that we can actually derive from these 3 axioms. The first one is called the chain rule. Right? So probability of x and y can be written as x given y times y, or y given x times x. Okay, we use this in various applications, including, for example, the pixel RNNs that I'm going to talk about next lecture. The second one is called the total probability theorem, I think. Yeah. So here, I basically introduce a new variable y, and I say, if I basically add the joint probability of x and y for all the possible values of y, then what I should get at the end is the probability of x. Okay? And I can also write the joint probability of x and y due to the first theorem as x given y times y. Okay? And that basically gives us the Bayes law. From here I can derive the Bayes law, which basically says, y given x can be written as x given y times y, divided by some normalization constant. Now, usually people don't pay attention to this normalization constant because it's just a normalization constant, but we'll see that it actually has a very specific meaning when it comes to machine learning and data modeling. So let's pay attention to this. So upstairs I have x given y and y. This is sometimes called the prior. This is called the likelihood. And down here I have just probability of x. That's my normalization constant denominator. This is called the evidence. And it can also be written using the theorems above as a sum, whose terms look like the denominator, but you basically have a sum over all possible y values. So take a look at this slide, try to remember things, and ask me a question. You have 1 minute for questions, because if you have some questions on this slide, the rest of the presentation is going to be very difficult to follow.
What does H stand?
H is our all the assumptions that we have. So according to the sort of Bayesian way of doing probability, there is no unconditional probabilities. Every time you mention a probability, you're basing it on some information, and H stands for that information. So in the particular case that we're going to use this in, H stands for the model set. So if I'm using, a linear model, then H stands for all possible linear models, etc. Ideally, H should stand for any possible model, but that's kind of hard to represent and take integrals over and stuff. Any other questions? Okay, so it turns out probability has some really neat properties, like being the only logical thing if you want to do some logical inference. I'm not going to get into the details of that, but basically when people come up with alternatives to probability like fuzzy sets and stuff, you can basically argue that you don't need any of this, because if you have uncertainty in the world and if you want to act according to some rational rules, probability axioms are the only ones that satisfy those rules. Okay, so now let's customize the general probability laws that we've seen in the previous slide to the specific case of machine learning. So here I'm going to say theta is my parameters, all the weights in my neural network, let's say. D is my training data, and H is my model set. Okay, so H basically refers to all the neural networks, or whatever the model set we're thinking about is. So in this case, we can basically use the Bayes law to write something like this, which says, well, I have a model set H in the beginning, and somebody gives me some data D. What do I know about my parameters, right? So that's basically the problem of training a model in machine learning. So what do I know about parameters? Well, I don't know exactly what the parameters are. That's the main difference between probabilistic thinking about this versus the machine learning we've been learning so far. In the training algorithms we've learned so far, we say, oh, there's SGD, and it optimizes something, and at the end I get one best theta, right? So here we actually accept from the beginning that we will never know the actual theta. We can only know some sort of probability distribution around that theta, and that probability distribution depends on how well different parameters actually can generate the data that I'm observing. Okay? So to put that in math, probability of data being generated by a particular set of parameters is known as the likelihood. That's the first term. The probability that I'm actually using these parameters from my model set, theta given H, is known as the prior. So maybe I think, for example, that very large weights in neural networks are unlikely a priori before I see any data, so that would be part of the prior. Okay. And finally, the normalization constant, probability of seeing this data set, assuming that this is the right model set, is known as evidence, probability D given H. Questions? Now, back to regularization and why regularization might work. So, so far we've always maximized likelihood, or log likelihood, or minimized negative log likelihood. We only work with likelihood, right? So we basically found the theta parameters using SGD or Adam or whatever, that basically gave us the best likelihood. We ignored the rest of this equation. Okay? And because of that sin, we have all these problems of overfitting and underfitting, and we don't know what we're doing, etc. Okay? So if you use the actual regular probability theory, we would not have an overfitting problem, for example. So note that there is a probability of theta given h. In particular, we haven't used. And it turns out that that's one way to understand regularization. For example, if I assume that probability theta given h is a Gaussian, so in the beginning, I basically pick I'm assuming my data has been generated with a neural network, and the weights of this neural network have come from some Gaussian distribution. That actually turns out to be equivalent to L2 norm regularization. Okay? So if you work out the math, multiplying the likelihood with a prior and multiplying, adding to your negative log likelihood, some regularization based on the L2 norm of your weights are the same thing. One is the log of the other. So regularization can be understood as adding some prior to our weights, which helps us a little bit in the direction of overfitting. Yeah.
Gaussian, like the square limits.
That's right. So in Gaussian, you have e to the minus w squared. And if you take the log, that gives you w squared. And w squared is what you have there. And then L1 regularization corresponds to the Laplacian distribution. And if you actually take the log of the Laplacian distribution, you get the absolute values of the w's. So they can be understood as applying these priors. So using likelihood with prior or with regularization is also known as map estimation. You might come across this somewhere. So that's maximum a posteriori estimation. What does that mean? We were doing maximum likelihood estimation. We were only noticing this term. Now we're noticing these two terms and maximizing this, the posterior. So that's why it's known as maximum a posteriori. Okay? Questions? Now, last thing before I skip this slide is I should never, the answer to the question, what do I know about theta after observing this training set, is not that theta is the maximum likelihood value or theta is the map value. Those are both wrong answers. What I know about theta is basically theta has that distribution. Okay? Now this distribution might be very peaked, in which case approximating this with the central value might be a good idea, but it might also be very wide, it might be multimodal. Okay? So theta, after I observe the training set, can have very, very different distributions, and representing that distribution as if it was a single value is always a mistake. We only do it for mathematical convenience, and we pay for it by overfitting. Okay? So the real answer of what do you know about theta is that you basically know the distribution. So what do I know about future data? How do I do predictions? So I observe some past data, I have a model set, I have some theta estimation, I trained my model, let's say, I'm doing future predictions. What do I really know about the test set? Well, what do we do in regular machine learning? We take the training set, we train our model, we find one best set of weights, which are the maximum likelihood weights, we hope, if the optimization worked well. And then we use those weights to estimate the instances in the test set, right? That's also wrong. Why? Because we should never assume that there is only one best weight. We have a distribution of weights, and they have different probabilities, posterior probabilities. We should use all of them, okay? So if somebody asks us about some future data, so let's say I have an unsupervised problem, so I'm just trying to guess the probabilities of X given training data and the hypothesis space. The real answer to this from our probability axioms and theorems, is an integral. So it's a summation. It's a summation over all possible values of theta. Okay? And we basically take the prior probability of theta, how likely this theta is before we saw any of the training set, and, sorry, after we saw the training set, this is the posterior, I misspoke, and then we ask how likely is x, this new thing I'm looking at, given this particular parameter, and I basically add these things up for all possible theta, and that's the real answer for that future estimation. Okay? So all of these follow from the axioms of probability. So you know these things are the correct results, and everything we've been doing so far are trying to approximate these. So this is also an important slide, so I'll give you a minute to look at it and ask questions. Yeah.
Is this something done only out of theoretical curiosity, or
No, there are people who implement Bayesian neural networks and find ways to approximately train them.
does it give better solutions?
Yes, in some problems they do.
So by d theta, do you mean taking a theta vector and implementing and getting results and putting that in a table of probabilities? This data basically,
What
does this
so-
procedure tell us?
forget about d theta, turn this into a sum in your head. So this is a sum over all possible values of theta, of how likely this theta is after seeing my training set, and what probability does it give to this new example. So you're basically averaging over all possible models that could ever be. You're averaging each of their answers, if you think about it. So normally what we do is we train a single model and we ask for its answer. Instead, we're going to ask the answer of each possible model with each possible weight matrix, weight array. But we're not going to take all of their answers equally. We're not going to weigh all of them equally. We're going to weigh the answer that each one gives with the posterior probability of that particular theta given the training set. So how well did that theta explain the training set? That basically becomes its weight. And then we use those weights to average all their answers. So you can also think about this as a sort of ensembling method where we're actually ensembling over all possible models. But we're weighing them differently based on how well they did on the training set.
So this is like ensembling, but it's impossible to integrate over all the theta.
Correct.
So I'm trying to select some theta, let's say. I would select the maximum posterior probability theta.
Correct.
But I would also make sure that they are independent somehow.
Correct.
But how would
So
I do that?
there's a couple of different methods to approximate this. One family of methods are called Monte Carlo methods. So Markov chain, Monte Carlo, and other sampling methods allow you to sample from this distribution independent theta values. And instead of taking this integral, if you have a program that can give you samples of this p theta, then you can take 10 of them or 100 of them and approximate this integral. Okay? And there's another set of methods called variational methods, which basically have an analytical approximation to these integrals. So it is true that, the only downfall of Bayesian methods is their computational complexity, so we invent these approximations or randomized methods to approximate the results. So 2 questions have been answered so far. What do I know about the parameters after seeing the training set? And what do I know about the test set answers after seeing the training set? And the thing to notice in both questions is that we never talk about a single best theta. We always assume that theta has a distribution. Final question. How about my model? How do I know that linear model was right or a single layer neural network was right? Okay, so what about H, my model space? How do I actually judge how well H is chosen according to this data? So let's say we have 2 different model spaces, H1 and H2, let's assume H1 is all the linear models, okay? And H2 is all the single layered neural networks with, I don't know, 64 hidden units or something, okay? So they're different model sets. How do I know which one to use? Before we said, oh, there's bias and variance and there's a sweet spot, so you should optimize it, etc., etc. So here's a probabilistic answer to that same question. Probability of H1, given the data set I'm looking at, is basically can be written as the prior probability of H1 and how well H1 is explaining the data given H1. Same thing can be done for H2. So the ratio of the probabilities of these two things can be used as a way to judge which model best explains the data set I have. Okay? And if you actually do this calculation right, you will not necessarily get the most complicated model. This calculation will automatically balance the overfitting and underfitting and give you the model that really best explains the data. Okay? We'll see some simple examples of this. Now, on the right-hand side, we see, I mean, this is just Bayes' law, and the denominators cancel. On the right-hand side, we see probability of linear models and probability of MLP models. The priors, you can basically make that up. Let's call these 50-50, so they cancel out. So here's the important thing. How do we calculate this? Probability of the training set given a set of models, not a single model, but a set of models. Okay? So given a single model, I know how to calculate the likelihood of the data set. But given a model set, just given the fact that this was a linear model set, how do I answer the question, what the probability of my training set is? Well, if we open this up, it turns out this term is exactly the term that was in the denominator of Bayes' law, okay? That we always ignored. So if we go back to Bayes' law, you see the denominator where it says probability D given H. So that's exactly the thing that I need in order to compare two models. And it turns out it's another, we can also express it as another sum or integral over all possible parameter values of the prior probability of picking that parameter from H and how well does that parameter explain my data set. So this is another one of these intractable integrals that we need to deal with if we're going to work with Bayesian methods.
So for the second shape, for the right side of the equality at the bottom, for the second term, you assume that theta is distributed according to normal or
Right, so I called this term the prior in the first slide. So the prior is basically, so when you talk about an H not only represents a set of models, but also represents a probability distribution over those models, which basically gives us the prior. So for example, when I say take H to be the linear models, I'm also saying assume some sort of probability distribution, prior probability distribution over the linear parameters. Okay?
You just assume they're 50-50 for the probability of linear models and probability of neural networks, for example.
It turns out that's rarely relevant because the difference on the second terms are going to be so big that the initial thought about H1 and H2 will just be unimportant. I mean, these terms will be millions or billions apart. And if you basically have this term to be 1%, 99%, 50-50, whatever, it's not going to matter that much. Any other questions? Okay, so here's in big font, big letters, one thing that I want you to remember after this lecture. Okay, so if we could use all of these things, if we could actually do, if we had infinite computational power, if we could do these integrals exactly, use actual probabilistic inference, meaning we can integrate over all the parameters and all the models, then there would be no overfitting and no underfitting. We would actually always give the optimal answer to every question. Okay? All of these issues that we've been dealing with and trying to solve with regularization and dropout, etc., are symptoms of the fact that we're choosing one model. And we're ignoring that we're not actually sure about this model. This model is part of a distribution, and there's other possibilities in this distribution. Ignoring that results in all these generalization problems that we've seen. Unfortunately, doing this is computationally intractable. So that's why, but we can still try to approximate them. So here's some examples on the sinusoidal example. So, for example, instead of, remember when I had 10 points and a degree 9 polynomial, there were huge amount of overfitting, right? So small differences in the blue dots cause this curve to vary widely. What if I used a Bayesian approach? What if I said, okay, my model set is the 9th degree polynomials, but I'm not going to just pick one model. I'm just going to do these integrals and stuff and consider all possible models, all possible 9th degree polynomials. And I'm going to start with a prior for the 9 coefficients. Maybe, I'll pick them from normal Gaussian or something. And then I will calculate the posterior. What do I believe will happen after I see the data? If we did that, this is the result we get. The red curve is the result we get, and the pink shaded region around it is the plus and minus 1 standard deviation around the mean. So this is the answer to the predictive distribution. This is what I derived with using this. Okay, so this formula basically says predict unknown data using an integral over all possible parameters, all possible 9th degree polynomials. Okay, so calculate the posterior probability of these 9th degree polynomials and tell me where they think the next x or y is going to be, and integrate them. And if I do that, this is what I get. Okay, no overfitting, no bad behavior, summarizing exactly what I think I know. And if instead of using 9th degree polynomial, if I use the 12th degree polynomial, I would get something very similar. It would not wildly start swinging, because I'm not picking one curve out of many. Here's another example illustrating the fact that the scary case for all machine learners, the case of having very few data points, is not a problem if you're using Bayesian methods. Okay? So even if you have one data point in a Bayesian method, look at what happens. The single data point basically gives you a predictive distribution, gives you a distribution for future data that is centered around 0. Okay, the red line is 0, which we said is bad. But the pink, the 1 standard deviation region around that, as you see, is getting wider and wider the further you go from that blue point, which basically exactly coincides with our intuition. I know that around that blue point, I'm fairly sure where the y values are, but as I get further and further away from the blue point, I have no idea because I only have one data point yet, right? And here is the same curve for 2 data points. Again, the red curve fits those 2 data points, but the pink region around them, the 1 standard deviation of the predicted distribution, gets wider and wider the further away I get from the data points. And the more data points I have, the narrower the standard deviation gets. And at this point, after seeing this much data, I'm saying, okay, this red curve is the mean, and the pink region is the 1 standard deviation around my predicted distribution now. Okay? So this way of looking at things not only gives us sort of sensible results, it also tells us how uncertain these results are. Compare that what we do with a regular neural net. We basically give a new x, a new image, and we ask for some y. And we take that y and we don't know how uncertain it is, Was the neural network sure about this y, or was it in an uncertain region? We don't know anything about that, right? A Bayesian model will also give you a confidence interval around the answer. And if it's not sure, that confidence interval is going to be large. Here's the same thing. If I omit a couple of the points on the right-hand side, you can see the pink region growing. These were all predictive distributions. You might wonder what happened to my theta. Okay, so what if I basically took the posterior distribution? Remember, posterior distribution is a distribution over theta. Predictive distribution is distribution over my data points. Okay? Posterior distribution basically tells you something like this. So the first picture says, after seeing only one point, using a model set of, I think these are Gaussian processes, I'm not sure, some model set, doesn't matter. If I calculate my posterior distribution of the coefficients for this type of model, and if I randomly sample from them, okay, I get these red curves after seeing one data point, because they're all over the place. The only thing they can agree on is they're close to the blue dot. Okay? If I see 2, I get that. If I see 4 points, I get this. And if I start seeing many, many points, they automatically basically shrink down and start fitting the data fairly well. Okay? So this was the representation of the posterior distribution. This was the representation of the predictive distribution. Any questions about the predictive versus the posterior? Okay, let's skip this. I have 5 minutes left. Let's see if I can do Mackay. So, when two models are equally good on a training set, we tend to prefer the simpler model. And scientists do the same thing. If two formulas explain some natural fact, they tend to pick the simpler one, etc. And that's known as the Occam's razor. When all else is equal, the simplest explanation that fits the data is the one to use. Now, why is that? Right? So philosophers have been discussing this for ages. Here in this example, here's a little picture, and there's a tree, and there's this thing behind the tree. Is it 1 box or 2 boxes? Okay, so unless I ask this question, you look and you're pretty sure that's 1 box. But now that I actually told you there might be 2 boxes, you're basically saying, that's not very likely because they're not going to exactly align and be the same height and color, right? So what gives you, so it's very intuitively embedded in us to go with the simplest explanation, but why is that really? So aesthetic reasons, empirical success, it turns out there is a mathematical justification for this if you think about it in terms of the Bayesian logic. So, in this graph, the x-axis is not a single number, but it represents all possible data sets. Okay? So if I have a data set of, for example, 60,000 MNIST digits or something, the d-axis here represents all possible 60,000 MNIST digit data sets there can be in the whole universe. Okay? So it's a very big axis. But in order to make my point, I need to fit this into a single axis. Okay. Now, I have 2 different model sets, H1 and H2. And let's say one is a linear model, the other one is a deep neural network model. And if I actually think about my data coming from these different model sets, the larger model set will be able to generate or fit a wide variety of data sets. Whereas the simpler model can only generate or fit a restricted set of data sets, okay? Number of data sets. So to make it more concrete, let's take regression. let's say we're generating and predicting data sets like the sinusoidal example, and H1 is all the linear functions, and H2 are all the 10th degree polynomials. Okay? So the linear functions are always going to give us these straight lines plus minus some noise. So very restricted set of data sets that we can hope to observe if the linear model is true. Whereas a 10th degree polynomial can also give those by setting 9 of its coefficients to 0, but it can also give us a lot more. It can give us, wildly varying, swinging data sets. So this is what's basically being represented here. So C1 is all the data sets that H1, the simpler model, can give us. And this C2, there's no C2 here, I guess, but this other distribution is the ones that the more complicated model can give us. So any questions so far about the x-axis and what these curves mean? Now, I'm talking about probability of a data set given H2, probability of a data set given H1. And these probabilities have to add up to 1 because of the axioms of probability. Okay? So if I'm a more complicated model set, then I need to distribute my probabilities over a wider range of data sets. And if I'm a simple model set, then I can concentrate all my probability into a smaller range of data sets. Okay? So these curves, the area under this curve and the area under this curve, both have to be 1. Therefore, the curve with the narrower base is going to be higher. Okay? So the individual probabilities that it assigns to the data sets in this region are going to be higher. All right? So now, I ask you a question like, okay, if my data set is this, is it, coming from H1 or H2? Well, you look, probability of this data coming from H1 is almost 0. Probability of it coming from H2 is, reasonable. Whereas if I ask you the same question here, you immediately choose H1. Why? Because H1 has a much more restricted set of things that it needs to distribute its probability over. And if you happen to see as your data set one of those things that are consistent with H1, then you prefer H1, simply because probability of data given H1 is higher. Okay? So this is basically why Occam's razor is true. Why you prefer simpler models that are consistent with the data set you have seen. So, questions? The rest of my slides is basically elaborations on this, and you can go over it and ask me questions in the next lecture. But basically this was the picture I wanted you to understand. Okay?
By evidence, do you mean a specific D?
Evidence is basically probability of D given H. So this term is known as evidence. Probability D given theta is known as likelihood, but probability D given H is known as evidence.
I have a question about this overfitting and other things. So if we had all the models, you said we wouldn't have overfitting.
Correct.
But we would still estimate models with respect to the data set.
Correct.
So
We wouldn't estimate one model. We would actually understand the true distribution over all the models, and you would get something like this, right? So, or something like this. Where's the? Yeah, this is the one I wanted to show you. Yeah. So, this is the exact same case where we overfit before, where the red curve was wildly swinging before. Instead, because that we picked one of the red curves and we said this is the right one, and that's what calls overfitting. Instead here, we're basically saying look at all the possible red curves and tell me where they're located, where their mean is, where their standard deviation is, weighted by how well they explain the blue dots. Okay, and if you do that, then this is what you get. You get the mean at the red curve, and you get the standard deviation of the pink.
But these blue dots are training set, right?
Yeah, the blue dots for training set, yes.
What if the training set is coming from another distribution?
I don't know what distribution it's coming from. You mean something that is not in my model set, so I have a bias.
Yes.
So Bayesian methods will not fix your bias, right? So if the data is not coming from a linear model set, then modeling with linears is still going to underfit. So it's not a problem for underfit. It's not a solution for underfit.
Okay.
Still, well, I wish I had the picture to show you. I'm going to also say that a Bayesian linear regression does not give you a line. If you run Bayesian linear regression on something, you will get many, many lines. And if you plotted the middle part of all these lines, the mean of all these lines and the standard deviation, you can get something that is not a line, that's actually curved. So it might help with underfitting that way. Questions? Okay, see you next time.